My name is Scott Stoltz. I'm one of the founders at OSC, and I'm privileged to introduce Mayya Sharipova. She's a Java engineer at Elastic. She's focusing on current and future enhancements to search features in Elasticsearch. She's passionate about making search smarter and cool things that are built on top of it. Today she's going to talk about vectors in search, and is a little bit of a side note. She just put a patch in recently that I think actually the excitement from that bubbled through our whole office and probably the Solar community, because I think the effects of it are going to be felt across the board. So I'm really happy to hear this talk. Thank you.
Hello everyone. Yeah, thanks for introduction, Scott. Actually, my talk will be a little bit broader than just vector fields. We've recently done at Elasticsearch several new developments on how to use numeric features in Elasticsearch, not only vector fields, but also some other features. And I would like to talk today, to introduce them today to you. And what specifically I will talk about rank features, fields. I will talk about new query that we have, distance feature query, and about vector fields. Now, let's begin first with problem statement. So many people use Elasticsearch to find with text queries. So queries something like, I want to find news on stocks or stock markets. I want to find Japanese restaurant, or I want to find help articles on the topic how to zip up files. And these queries are well researched. They're based on the this BM25 model and use what we call text scores, organic searches. But very often, users want to tailor their search results and augment the text scores with some numeric features. And these numeric features could be anything depending on your application. For example, you want to say, I want particular news on particular topic, but I prefer news on my favorite topics from reputable sources. So I want this kind of news come up first in the search results. Or I'm looking for a Japanese restaurant, but I prefer restaurants closer to my location. Or I'm looking for the help on articles how to zip up files, but also want results on all semantically similar topics. So this is kind of three types of searches: recommendation, proximity search, and similarity search. And we introduced three new features in Elasticsearch that we can think that can help you with these kind of three scenarios. So for the first case, we have rank features fields. For the second, we have distance feature query. And for the third one is vector fields. And in my talk, I'll talk a little bit in more detail about each of these features. So first, about rank features. So we had a lot of asks from our users on the effective ways to combine this query-dependent text score with query-independent numeric features. And these numeric features could be anything. It could be, for example, page rank of your article, or it could be URL length of your article. And we were thinking what would be the good ways to do this combination. And our engineers found a paper that discusses it and presents and kind of shows the best ways to combine this query-dependent scores with query-independent numeric features. And what this paper is telling, that the best way to combine text score with numeric features is through this linear combination, where you also do some transformation on a numeric feature. And three transformations that are presented: saturation, logarithm, or sigmoid. And for example, this is the, on this slide presents the kind of formula for saturation, where you get a value of your numeric feature and divided by some value plus pivot. And we have implemented kind of this paper in what we call rank feature, and I will show how they work. And also this, the query that work on rank feature is an optimized query that can skip non-competitive blocks. A little bit on this, a little bit. We'll also talk about it later on what it means. So, for example, I want to index my news article. I define kind of two types of fields. One will be page rank, and the type will be rank feature. Another is topics, which is the type will be rank features. So why one is feature and another is one features is because a document may have different topics, and I don't want to introduce, because it's quite sparse feature, and I don't want to introduce a lot of fields just for different topics. And then basically I index my news article. So I have this article on Toronto Stock Exchange. I define page rank for it, whatever I calculated based on your application. Define what is the topic. So this is like business 20 and Canada 50. Index another article. It will have page rank 42.3 and topics business 24 in USA 40. And then I can run special type of query called rank feature, which is usually put in a should clause of your Boolean query in order so that you can kind of boost your main scores, text scores that you get from document with this rank feature query. And you define what is your feature that you are boosting on. In this case, it will be topics business. And define what is the transformation you want to have and the parameters of this transformation. In this case, it's sigmoid. And also optionally supply boost that you want to have. By default, we use a saturation transformation. So for example, if I run this query, I will get my 2 hits. And in this case, I'm only boosting on this feature topics business. And so the articles that have higher business value as a feature will come out as first as top results. I can combine this feature. So I live in Canada. I'm more interested in the topics, news topics on Canadian topic. And if I apply these two features, 2 rank features query, the news that are on business and Canada, they will come out first. Going back to kind of our original question on recommendation, so find me news articles on particular topic, but I give preference on my favorite topics and also from reputable sources. The way we can model this kind of search problem in Elasticsearch is through kind of must query and then should query on all this, using all these rank features. So my favorite topics, it's topics business, topics Canada, and I also give preference to articles from reputable sources, which I model as a page rank. So, and in this case, the articles that kind of satisfy this query and will come out first, and the articles that have high values of all these features, they will be boosted and will be the top results. So I also mentioned briefly that this is a very effective query because it allows to skip blocks of non-competitive documents. And this slide a little bit explains what it actually means in Elasticsearch. So the way we index, this slide shows how we index documents in Apache Lucene. We index documents by blocks, and this is basically, so you can see every block has first 128 document IDs, followed by 128 frequencies, and by a data structure what is called skip data that allows you to quickly skip to other blocks. And from Elasticsearch 7.0, we started to index what is called impacts. And impacts basically tell you what is the largest score that could be produced by that block. So how it's helpful, so during search request, if you already have a set of documents and you know what is the score in these documents, then you can quickly ask every block what is the maximum score at your block, and if it's like less than what I need, I can quickly skip it, so I don't need to read every block and process it. And this allowed us to make optimization speedups up to like 10 times for some types of queries, and you may notice it from Elasticsearch 7.0 version. And this is what also these kind of impacts are also used for rank feature query, because these rank features, they're indexed in a special way. There is only kind of one, underneath only one Lucene field is created. It's called feature, underscore feature. And these numbers that I was showing you, they are indexed as term frequencies. So we can quickly ask every block what is the maximum kind of feature on your block and quickly skip them if it's not like what we are looking for, if it's less than what we have. And this allows this type of query to kind of to be quite efficient. Okay, this was about rank feature, and another kind of new feature I would like to introduce is called distance feature query. And this will allow us, this will help us with this proximity or recency boosting. So we often need to boost document score based on proximity or recency to some given origin. And in Elasticsearch, if you kind of worked with dates or geo points, you know that you can filter. There are queries that allow you to filter documents based on geolocation or based on the date range. But this is just filtering, so you cannot kind of produce scores for this type of queries. There is a function score query where you can write kind of a script that kind of allows you to do this, but it's a little bit more kind of expert way to do this. And it's also maybe not that performant. So distance feature query basically allow you what is kind of addressing. It allows you to very efficiently, very performantly calculate the scores based on proximity or recency to some given origin. And here, kind of how the score is calculated. You define a pivot divided by pivot plus distance, and the distance is basically origin that you give in a query, and minus documents value, absolute value from this. And this produces scores from 0 to 1. 1 means that the document's value is equal to the origin, so it's the closest to the origin. And 0.5 will mean that the document value is distant of pivot from origin. So basically, by defining your own pivot, you can control how much scores should be decreased as you go further and further from the origin. And this query is also very performant. It allows to skip non-competitive hits. But because it's dynamic, we need to dynamically calculate, it's not that performant as rank feature query. And here, example that kind of addresses our second problem, which is find me Japanese restaurants, but I prefer restaurants closer to my location. So I model it as a bool query. I have a must clause with a type of Japanese restaurant, and then I boost documents by should clause with this distance feature query. I defined my field, which is location of my document, defined my origin, where I'm located, and my pivot is 1,000 meters. So every kilometer, the score will be decreased by, after 1 kilometer, the score will be 0.5, and the maximum score that this query can produce will be 1. And then after running this query, I'll get results. And as you see, the restaurants that are closest to my location, they will come up as top results, as top hits. So this query, you can also use it for dates. So in this case, it will be kind of boosting by recency. So you can define a date, for example, now, and bring up, for example, news that are closest to the current date. This was distance feature query. And the last thing that, the last feature I would like to introduce is vector fields. So how it started, we also kind of had asks from our users to a way to index and store and do some query manipulations on what is called vector fields. So vector fields is basically vectors. It's arrays of float values of many dimensions, and they can represent whatever is relevant for your applications. For example, it could be features, it could be images, it could be word embeddings. And we have introduced two field types. One is dense vector that allows you to store vectors of float values up to 1024 dimensions. And one is sparse vector that allows you to store sparse vectors of float values up to 1024 dimensions. And the way we index them is basically just a blob that is indexed in the Lucene binary doc values. And we kind of decode and encode them when we run queries. And kind of two things to be careful with is first your index size, because for every document, like for every field, number of bytes that it takes, it's 4 times by number of dimensions. So if you have like 1,000 dimensions, then for every document, you kind of need to allocate 4,000 bytes for every document. And for sparse vectors, because we also store kind of dimension value, then it will be kind of 6 bytes. And the way they're queried is there are 2 predefined functions in painless script that are accessible through scripts core query, cosine similarity and dot product, but there are no any optimizations. So it's a sequential scan through all the documents. So if you have a lot of documents, millions of documents, so you kind of should be careful with it. Otherwise, your queries can run for a long time. So how this field is used? You can define a type-weight dense vector. So I have my index with 2 fields, title and title vector. You use any external tools that you like to encode your text. For example, here I encode my vector, my title, and kind of index it. And then there are, as I said, there are 4 predefined functions for sparse and dense vectors that you can use. For example, cosine similarity allows you to calculate cosine similarity between your query vector that you give and all the document vectors. And of course, the vectors that have the smallest, the largest cosine similarity will be kind of will be the top results. For example, here I have a query that kind of I have cosine similarity. I'm giving my query vector as a parameter to script, to painless script. And then I calculate cosine similarity between my query vector and all the vectors from the doc title vector field. I also do +1, and the reason is that from Elasticsearch 7.0, we don't allow any negative scores. And because cosine similarity can start from -1, so I make sure that my query produce non-negative score with this +1 kind of operation. engineer, Julie put a project where you can see how dense vectors can be used for text embeddings. So for this, we use Google Universal Sentence Encoder that can encode your text and produce kind of vector from it, which represents text embeddings of this text. We index a small data set of 2,000 questions from Stack Overflow data set, which are encoded as a dense vector in Elasticsearch. And for query sentence, there is a script that she put, like you can put your query sentence that will first will be encoded, again, using this Google Universal Sentence Encoder as a query vector, and then put it in a query for Cosine Similarity function. And because it was quite small data set, the performance was very good. The query performance was less than 50 milliseconds, but it was a small data set. Going back to the third question, question, similarity question that I have, find help articles on the topic how to zip up files. So the way how I can address this with Elasticsearch query, so I have I can have the script score, define a script, and calculate cosine similarity between my query vector and all the document vectors. And kind of as I see it, I will get the results. And if you see that even though my query was zip up files using this similarity, it allowed me to find documents that don't share the same keywords. For example, the first result was compressing, decompressing folders and files, which have mostly different keywords from the keywords that I had, like zip up files. But also be careful that sometimes you may find irrelevant results. For example, the document number for searching directories for tons of files may not be relevant to the topic that you kind of were searching for. Another thing is that if you want to, you see that part of the script score has a query. So if you have a very big data set, you might want to limit, to filter the documents that you need to run your cosine similarity or other functions or dot product, so that you don't kind of, so that your query will not take a lot of time. And now to summarize. So basically, this is 3 features that we introduced recently in Elasticsearch that can help you to work with numeric features. One is rank feature, where you need to create a special type of fields called rank feature or rank features. Another is distance feature query, which works on already existing fields, date, nanos, and geopoint. And another is vector fields, which is also require a new field type, dense vector and sparse vector. For search, for rank features, you have rank feature query, which is very optimized. It can skip non-competitive hits. Distance feature query for distance feature query. It is also optimized, but it does some dynamic calculations. And for vector fields, we have script score query with similarity function, and it works as a sequential scan. And possible usage scenarios, how they may help you for your applications. So for rank feature, you can use it for recommendation, for example. Distance feature query allows you to do proximity or recency search to boost documents on proximity and recency. And vector fields can help you with a similarity search when you want to find some similar documents that may not necessarily share the same keywords. They all license under Apache, and Elasticsearch version they available is from 7.0, which is already out, or 7.1, which will be out soon. And this is the reference, and the last reference is the GitHub project that Julie put out, how you can see how they can be used, vector fields with text embeddings. And that's the end of my presentation. Thanks very much.
Thank you. Hello. There we go. Okay, questions?
So this is a question related to your distance features, specifically, I'm sorry, rank features, specific to recommendations, but something of a unique variation on it, where two people or two documents, if you will, need to be similar or agree and be used together. Use case would be something like finding a publisher associated with a writer where both the publisher and the writer agree. So it's sort of a two-sided market issue. Do you think rank feature fits within that domain?
So you just, is it the same values that they share between?
It's potentially a longer topic discussion, but effectively you're trying to match people together who agree to work together. So you want to show some from a publisher's perspective, what are the list of writers that they are compatible with, and that the writers are interested in having their book published by that writer.
Mm-hmm. And compatibility is decided by the how some features match, yeah?
Yes, but it's also important to essentially predict, typically through machine learning, that the publisher is shown writers that are compatible with that publisher.
I see, yeah.
We could talk about it offline if it's a longer.
Yeah, actually, yeah, I think that rank features and distance feature queries basically mostly to boost documents or like in your context people. Yeah, I'm not sure how it could be applicable for this scenario, but maybe we can discuss offline how
Thank
it's
you, appreciate it.
what could be the way to do that.
All right, I'm gonna follow Renee's example. Any questions on this side before I migrate over there? I'm going. Anybody over here? I think everybody's still a little sleepy from lunch. All right, thank you, Mayya. That was wonderful.
Thanks.